Bismillahirrahmanirrahim. This video will be talking about fixed bias configuration of field effect transistors. We have done another question, example 1, in my previous video. In this video, I will be discussing end chapter question number 1, 7.2.1. Now we have learned all these. I'm just repeating. This is the Shockley's equation, a very important equation that we're going to use. This is the circuit diagram, and again Shockley's equation. Important point is the gate current here. In FET, we assume that the gate current is approximately 0, and therefore the drain current is equal to source current. ID is equal to IS. Then another parameter that are discussed is the transconductance curve. Now this curve is called the transconductance curve. It is also called transfer curve, and it is also called device characteristics curve. This is between VGS, this here VGS, and ID current. So ID and VGS. Now, and just to recall what is fixed bias, this configuration is fixed bias. And for DC analysis, we remove the capacitor open circuit. So our circuit will become like this. And then we say that the current IG is 0, therefore there will be no voltage drop here. So the circuit further simplifies to look like this. Now from here, if you take the KVL equation around this, then we can see that plus VGG is equal to plus VGS equal to 0. And from here, VGS is equal to minus VGG. That means this VGS is fixed by the value of VGG. And that is why it is called the fixed bias configuration. Now coming on to the question. Sorry, I have a bad throat. Please don't mind. So this is the question given. And one point in the this 11th edition, here the voltage is 14 volt, but in earlier editions it is 12 volt. And since I'm following one of the solution manual, which is using 12 volt, so we stick with 12 volt. But I am sure you can modify this. Instead of 12, you can always write 14 and solve this question. The question has 4 parts. Guess the transfer characteristics of the device and superimpose the network equation on the graph. Determine IDQ and VSDQ from the graph and use Shockley's equation to solve IDQ, and then compare the solution with part C. So let's come to the first part. Sketch the transfer characteristics. And we have already discussed that the transfer characteristics will look like this. It is between VG and ID. So we start with the Shockley's equation and take a couple of values of VG. Start with the blank curve. First we say that VGS is equal to 0 volt. So like we are here now at 0 volt. So putting VG 0, this will become 0. Therefore IDQ or ID is equal to IDSS. So ID is IDSS and IDSS given here is 12. Therefore at 12 we mark a circle. Mark a circle at 12. That's the first point. And the second point, okay, the second point will take ID to be 0. ID is equal to 0 when VP is minus 4 volt. This is VP is minus 4 volt when VGS is equal to VP. That means VGS is equal to minus 4 volt. So this is the point, and I is 0. So we mark a circle here. then mark the circle. Then we take another point, and that is we take VGS is equal to VP over 2. That is, in this scale, we take this point. VP was minus 4, so we take minus 2. At this point, ID, putting in this equation, VG and VG is minus 2, VP we know is minus 4. Solving, we find this to be IDSS by 4. So ID is IDSS by 4. IDSS is 12, so 12 divided by 4 is 3 milliampere. So when we are here, then we get the current 3 milliampere. So we mark that point here. This is the point. And we can draw a curve, but to be more accurate, we need at least one more point. And that point we are taking it to be VG is 0.3 VP. So 0.3 of this VP is minus 4. So it will be minus 1.2. So minus 1.2 will be somewhere here. And again, putting minus 1.2 and solving, we get IDQ is equal to IDSS into half. That is IDSS divided by 2, which is 6 milliamperes. So 6 milliamperes and 1.2 gets our fourth point. Now we can connect all these 4 points to plot the characteristics curve, transfer curve. So this is the first part done, part A. Now let's go to the part B. Superimpose the network equation on the graph, on the same graph. This is the graph, and this is our network equation. That means VGS is equal to minus VGG, and minus VGG in question is 1.2, minus 1.5. So that means at 1.5, this is 1.5, we have to draw a straight line. We drew a straight line. So this is only what it wants. Superimpose the network equation. So this is the network equation. Now it says determine IDQ and VDSQ. Now IDQ, this online, this is the question point where the network curve and the graph intersects. That gives us the question point or Q point for the drain current, which is approximately equal to 4.7 milliampere. This is from the graph. And now we can find VDSQ. The VDSQ is this voltage. So from here we can see that VDSQ is VDD minus this voltage drop. VDD minus IDQ RD. IDQ we have found from the graph. We'll put that value. It is 12 minus 4.7 and 1.8. That means VSQ is 3.54. So from graph we found these two things. So this is part C. Then part D, it says using the Shockley's equation. Now not from the graph, using the Shockley's equation, find IDQ and then find VDSQ. Okay, now the last part says using Shockley's equation, solve for IDQ and then find VSDQ and compare the solution of part C. This we had found from the graph, this result here. So this is the Shockley's equation. And this was the network equation. From that we found VGS to be 0.15. So we'll put that value here. So putting 0.15 and VP is minus 4. And solving, we find IDQ to be 4.69 milliampere. Now remember, in the graph we had found 4.7. Then we will, using the same formula, we'll calculate VDSQ, this formula. This voltage minus drop here. Only we are using IDQ as the calculated here. So VDSQ is 3.56. So if you compare, the VDSQ from the graph was 3.54, and from the equation, Shockley's equation, it is 3.56. Therefore, we can say that the comparison is very good. They are very close. I hope you have been able to follow this. Please let me know through your comments. Thank you.